Welcome to Askprep, your trusted companion for NEET and JEE preparation. Today we will study about a very important topic of chemistry, which is structure of atom, quantum numbers and electron configuration. Everything around us is made up of atoms, the fundamental building blocks of matter. But what exactly is an atom, and how do we describe its structure? To truly understand the behavior of atoms, scientists developed quantum mechanics, a theory that goes beyond classical physics and introduces new ways of explaining atomic structure. Central to this understanding are quantum numbers and electron configuration, which help us describe the exact position and energy of electrons in an atom. In early atomic models, scientists proposed that electrons move in fixed orbits around the nucleus, similar to planets around the Sun. However, later experiments showed that this model was insufficient. Instead of fixed orbits, electrons exist in regions of probability called orbitals, and their behavior is best explained using quantum numbers. Quantum numbers are a set of 4 values that provide detailed information about the position and energy of an electron in an atom. These 4 quantum numbers are the principal quantum number, the azimuthal quantum number, the magnetic quantum number, and the spin quantum number. Each of these plays a unique role in defining the electron's position within an atom. The principal quantum number determines the energy level or shell in which an electron resides. A higher principal quantum number means the electron is in a higher energy level, farther from the nucleus. The azimuthal quantum number, also called the angular momentum quantum number, describes the shape of the orbital. Orbitals can be spherical, dumbbell-shaped, or more complex, depending on this value. The magnetic quantum number tells us the orientation of the orbital in space, determining how it is arranged around the nucleus. Finally, the spin quantum number indicates the spin of an electron, which can be either upward or downward, playing a crucial role in the stability of the atom. With these quantum numbers, we can determine the electron configuration of an atom, which is a way of representing how electrons are distributed among different orbitals. Electrons fill orbitals in a specific order, following certain rules. One of the key principles governing electron arrangement is the Aufbau principle, which states that electrons occupy the lowest energy orbitals first before filling higher ones. This explains why electrons first fill the 1s orbital before moving to higher energy orbitals like to s to p and so on. Another important rule is Hund's rule, which states that electrons will occupy degenerate orbitals, those of the same energy, singly before pairing up. This helps minimize electron repulsion and stabilize the atom. Additionally, the Pauli exclusion principle ensures that no 2 electrons in an atom can have the same set of quantum numbers, meaning each orbital can hold a maximum of 2 electrons with opposite spins. Electron configuration plays a significant role in determining the chemical properties of an element. The valence electrons, which are the outermost electrons, influence how an atom interacts with other atoms. Elements in the same group of the periodic table have similar electron configurations in their outer shells, leading to similar chemical behaviors. For example, noble gases have fully filled orbitals, making them highly stable and mostly non-reactive, whereas alkali metals have a single valence electron, making them highly reactive. Beyond chemical properties, electron configuration also affects atomic size, ionization energy, and electronegativity. As we move across a period in the periodic table, atomic size decreases due to increased nuclear charge, pulling electrons closer to the nucleus. Ionization energy, or the energy required to remove an electron, generally increases across a period and decreases down a group. Electronegativity, which indicates an atom's ability to attract shared electrons in a bond, follows a similar trend. These periodic trends are crucial in understanding how elements interact and form compounds. One interesting application of quantum numbers and electron configuration is in spectroscopy, where atoms absorb or emit light at specific wavelengths. This phenomenon forms the basis of techniques like atomic absorption spectroscopy and emission spectroscopy, which help identify elements in distant stars, forensic samples, and even biological molecules. The study of electron transitions also led to the development of lasers, which have countless applications in medicine, communication, and industry. According to the Aufbau principle, electrons fill the lowest energy orbitals first before moving to higher ones. This explains why the 1s orbital fills before the 2s orbital, and why the 2p orbital fills after the 2s. The sequence of orbital filling follows a particular pattern that can be predicted using an energy level diagram. The Pauli exclusion principle, as mentioned earlier, ensures that no two electrons in an atom have the same 4 quantum numbers. This means that an orbital can hold only 2 electrons, and they must have opposite spins. Hund's rule governs the filling of orbitals within a subshell. When multiple orbitals of the same energy are available, electrons occupy them singly before pairing up. This minimizes electron-electron repulsions and leads to a more stable arrangement. For example, in the case of the p orbitals, each of the 3 orbitals will get 1 electron before any of them receives a second one. Furthermore, quantum mechanics and electron configuration play a critical role in modern technology. Semiconductors, which power electronic devices like computers and smartphones, rely on the behavior of electrons in different energy levels. The understanding of quantum mechanics has led to innovations such as quantum dots in display technology, superconductors for efficient power transmission, and even quantum computing, which promises to revolutionize data processing. By understanding quantum numbers and electron configuration, we can predict the behavior of atoms in chemical reactions, explain periodic trends, and gain insights into the nature of elements. These fundamental concepts form the basis of atomic theory and are essential for understanding more complex topics in chemistry and physics. The study of atomic structure has revolutionized our knowledge of matter, leading to advancements in fields like materials science, quantum computing, and even medical imaging. As we continue to explore the microscopic world, quantum mechanics remains a crucial tool in uncovering the mysteries of the universe. Thank you. This is Askprep, your guide to mastering NEET preparation. Let's decode complex topics and simplify your journey to success.